Welcome back, AP Chemistry students, to Unit 5, Kinetics. Today we will be talking about Unit 5.2, Rate Law Expression. So as our reactants form products, our reactants decrease in concentration while products increase in concentration. As our reactants collide with one another, they get used up and therefore there are less of them, so the rate of the reaction eventually slows. However, the reaction is constantly occurring as reactants form products. For most reactions, products can collide with one another and form reactants, so most reactions run in both directions. When this happens, at some point, the rate at which your products are forming reactants and your reactants are forming products becomes equal. This is known as equilibrium and is the subject of the next unit. However, talking about the rate at this state would be extremely complicated. And for that reason, this unit we are going to focus on the instant of mixing. At time zero, what is the rate of each reaction, either forward or reverse. Now this is done experimentally, so either we count how much gas is produced at the moment of mixing, we look at how much precipitate we get within a set amount of time, or we use the refraction of light through a solution known as spectroscopy to figure out how much product there is in a reaction. Since we have to look at data from an experiment, this means that if you are not doing the lab, I will be providing you with raw data that you have to analyze. So writing the rate expression is simply analyzing data to determine what the rate of a reaction is, or the constant by which that rate is determined by looking at the concentration of your reactants and how those reactants affect the rate. So rate law is expressed as rate equals K times the concentration of a reactant raised to its order. The order of a reaction relative to a reactant tells you how that reactant plays out in the reaction. Does it slow the reaction down? Is it the rate determining step? Or is it something that is irrelevant? So the order of a reaction simply deals with how big of an impact does this one reactant have on the overall rate. That's what an order is. Think of a reaction in steps, right? So let's say the reaction is to make a peanut butter and jelly sandwich. Your job is to spread the peanut butter and the jelly. Your sister's job is to put the sandwiches together, and your dad's job is to put them in a bag and put them in your lunchbox. Spreading peanut butter and jelly takes a lot longer than putting two pieces of bread together. So you are going to have a bigger effect on how fast you're making sandwiches. So your order in that reaction is going to be a larger number. You're going to have a bigger impact on the rate of the reaction. Now, orders of reactions can be zero or whole numbers, and in advanced classes, they will be fractions. However, in this class, we are going to focus on zero or whole number reactions. But it can only be determined experimentally. So the rate constant is simply a constant, a value that is used to get our overall rate. Rate is always a change in concentration over time, so the rate constant's units change depending upon the overall orders. Since you're taking concentration to some exponent, the constant's units are going to change depending upon that order. If concentration is cubed, you need to cancel out at least 2 of those molarities to end up with molarity for each second. So the units of K would have to be for each molarity squared seconds. We are going to talk a lot about determining the units of K at the end of this subunit. For right now, simply know that the rate constant is the value that makes it work mathematically so that you determine how fast the reaction has happened by taking into account the order of the reactants. So there are many different ways to determine the order of your reactants, but in all, an overall reaction's order is the sum of the exponents. So if we have a rate law that says that the rate of a reaction is equal to the constant times the concentration of A squared times the concentration of B to the 0 and C to the first, the overall order of this reaction would be 2 plus 0 plus 1, or 3. So we simply add up those exponents. So if you ever have a question that says, what is the overall order of a reaction? Simply add the exponents. So if something is zero order means that that reactant is not part of the rate determining step. It's not the slow step. Your father putting your sandwiches into a baggie and putting them in your lunchbox, that's not slowing you down. That doesn't have any impact on the rate of the reaction. So anything that is zero order, no matter what we do to the concentration, if we double it or even quadruple it, it's not going to affect the rate. The rate will remain constant. So anything zero order is not going to have impact on the rate of the reaction. So these are often the easiest to spot. If you double a certain reactant and the reaction's rate stays the same, that's zero order because it didn't have an effect. And if you think of it mathematically, anything raised to the 0 is 1. So if you have a reactant that is zero order and it's the only reactant, the rate equals the rate constant. First order reactions are the most common, and all nuclear reactions, for example, are first order. A first order reaction means that the reactant matches the rate. So if I double the concentration of the reactant, the rate doubles as well. And if you think mathematically, 2 to the first simply means that I doubled the amount I worked with. Or if I tripled the amount that I worked with, the rate would triple. First order reactions are, again, the most common. And all nuclear reactions are first order reactions. So if you look at a reaction and doubling the concentration of the reactant causes the rate to double, that's a first order reaction. Second order reactions are more common for gases, where if you double the concentration, the rate quadruples. Or if you were to triple the concentration, the rate would be 9 times as fast. So while this is most common for gas systems, please don't assume that all gas reactions are second order. That is just a generality. So again, second order reactions, whatever you do to the concentration, you square that amount. So if I double it, my rate quadruples. If I triple the concentration, the reaction moves 9 times as fast. Now there are 2 ways to analyze the data for what is known as the differential rate law. Differential rate law means that the data I give you is going to be rate versus concentration. I'm going to provide you the rate of a reaction based on the concentration of reactants. And you need to look at the reactants and how they changed in concentration and what that did to the rate to determine what their order is. And there are many ways to do that. Algebra is the most accurate. It will never fail you. It's just a matter of solving for the exponent. However, it does take time. You have to set up your rate laws. Please remember that a rate law will always start the rate equals some constant times your concentrations raised to your orders. This is always going to be the same for every experiment. So experiment 1, we're going to have this same setup. Experiment 2 will have the exact same mathematical expression. The only thing that will change between experiment 1 and 2 is the value of the rate and the concentration. So algebra simply puts one experiment over the other and cancels out like terms to determine what the order is. This setup does take time. You have to calculate things. However, it is infallible. Math does not make mistakes, and therefore, as long as you don't make mistakes, algebra is the surefire way, and therefore requires no extra explanation. However, it does take time. So if you have a kinetics question in the multiple choice part of your test, table logic is faster, as long as you know the definitions. And you might have to make some assumptions so you can get it wrong. If your logic is flawed, you will be wrong. Another problem with the table logic method is that you have to explicitly write out how you arrived at your conclusion. If you do not say things exactly as I phrase them to you, you will not earn those points. So, I'm going to show you both methods. Personally, I do not care which way that you solve things, and to be honest, if you are going for a 5 on the AP exam, knowing both is probably your best ticket. However, I am a fan of learning as little as possible and applying it to as much as possible. So when I was your age and learning this, I simply did the algebra. It never failed. I knew what I was getting. But I promise you only a 3 if you do that. If you're going for a 5, you honestly should be able to go both ways. So since I learned algebra first, I'm going to do algebra first. If you want to do the table logic method, which again is faster and just requires definitional terms, timestamps will be in the description below. So here we have data of rate versus concentration. We can determine the rate law from this data by algebraic terms, because regardless of what experiment we are talking about, as long as we have the same reaction occurring, the rate will always equal the constant times the concentration of A raised to some value times the concentration of B raised to some value. So since it's always the same, we can set multiple experiments equal to one another, meaning I can put experiment 1 and 2 and look for canceling out like terms. So when you do the algebraic method of differential rate law, find 2 experiments in which one concentration remains constant and the other makes a noticeable or easy to calculate change. So in experiment 1 and 3, the concentration of A doubles and B remains constant. So I'm going to use experiment 1 and 3 and try to figure out what is the order with regards to A. So to do this mathematically, I suggest you put the higher concentration as your numerator. So I'm going to put experiment 3 as my numerator. And again, experiment 3's rate. The rate is going to equal K times the concentration of A to whatever its order is, times the concentration of B to whatever B's order is. And I can set that equal to the rate of experiment 1. So with experiment 3 as my numerator, I can begin putting in some values. The rate of experiment 3 is 0.5 times 10 to the minus second. The concentration of A in experiment 3 is 1, and the concentration of B is 0.2, but that's kind of irrelevant. 0.2 divided by 0.2, regardless of what it's raised to, is going to cancel out. And regardless of what the value of K ends up being, it also is going to cancel out. In experiment 1, the rate is 0.5 times 10 to the minus second, and the concentration is 0.5. So I end up with 0.5 times 10 to the minus second over itself has to equal 1 to some value over 0.5 to that same value, or 1 over a half to some value has to equal 0.5 over itself. Well, 0.5 over itself is 1. So 1 divided by a half is 2. 2 to some number equals 1. So what can you raise 2 to? What can you raise 2 to get 1? Anything raised to the 0 power is 1. Therefore, the reaction is 0 order with respect to A. Now, all of that work is enough for me to simply come in here and be like 0 order for A. To determine the order with respect to B, it's the same setup. Find 2 experiments in which B changes, but A remains constant. In experiments 1 and 4, A remains constant and B changes. So I'm going to use experiments 1 and 4. Putting the higher concentration, experiment 4, as my numerator. A raised to the 0 is going to cancel out regardless of what we put in A, and the constant, by definition, is constant. So we really end up with the rate of experiment 4 over the rate of experiment 1. So 1 times 10 to the minus 2 over 0.5 times 10 to the minus 2 equals the concentration of 4, 0.4, over the concentration of 1, 0.2. So 1 over 0.5, the times 10 to the minus seconds cancel out, equals 0.4 over 0.2 raised to some value. 1 divided by a half is 2, and 0.4 divided by 0.2 is 2. So 2 equals 2 raised to some value. That value has to be 1. So the reaction is first order with respect to B. And yes, you would have to write that out. You can't just come in here and put a 1. But now we have our rate law. The rate equals K times the concentration of A to the 0 times the concentration of B to the first. One of the reasons I like algebra is because since I knew A was 0 order, I honestly could have chosen any 2 experiments because A raised to the 0, this whole column is irrelevant. I could have just looked at just the concentration of B in every single case. That is important because sometimes you will not be able to find 2 experiments where one of the concentrations remains constant. So algebra will never lead you astray. Table logic is faster. Table logic, however, requires you to know definitions, and if you don't have sufficient data, you might have to make some assumptions. Sufficient data means that you have at least 2 experiments where the concentration of each reactant is constant at some point. So here we have data sets where the concentration of A is constant in at least 2 experiments, while B changes, and the concentration of B is constant where A changes. So we have enough data, we won't have to make any assumptions. For table logic, we are going to determine the rate law by looking at the experiments, and we're going to look at 2 experiments at a time. In those 2 experiments, we're looking for a place where the concentration of the reactant we are looking at changes while the concentration of the other is constant. So, if we want to look at A first, in experiments 1 and 3, A changes while B is constant. So when A doubles, we need to look at the rate. If A doubles, how does the rate change? The rate remains the same. So since in experiment 1 and 3, the concentration of B is constant, while the concentration of A doubles, but the rate is unchanged, the reaction is zero order with respect to A. So we can say that the reaction is zero order with respect to A. If you choose to do table logic on a free response, you must write this verbatim. You must explicitly say what experiments you looked at, what was constant, what changed, and how did the rate change. And then you must say, with respect to the reactant you are looking at. All of that must be handwritten out when expressed. If you simply say the reaction is zero order with respect to A and don't tell me what experiments you looked at, or don't explicitly say B is constant, A doubles, the rate is unchanged, you will earn 0 points. So you must say all that. On a multiple choice, obviously it's irrelevant. You don't have to explain yourself, but in a free response setting, table logic requires you to say things explicitly to explain your logic. Let's move on and find order with respect to B. In experiments 1 and 4, A is constant while B doubles. So what happens to the rate? It looks like the rate also doubles. So when the concentration doubles and the rate matches, that's first order. So in experiment 1 and 4, the concentration of A is constant, while the concentration of B doubles. This causes the rate of the reaction to double. Therefore, the reaction is first order with respect to B. And again, you must explicitly say what was constant, what changed, how did the rate change, and what that means. If you do not say all of that, congratulations, you earn 0 points. So please, 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 if you do table logic in a free response, please write out your logic. On a multiple choice, it's a moot point, and so table logic is substantially faster than algebra. Kinetics questions on the AP exam are consistent. You'll always be asked, what is the order of each reactant? So that's maybe question A and B, or just A. Question C will ask you for the value of K and want the units. In order to determine the value of K, simply plug in any experiment into your rate law. So if we use experiment 5, for example, the rate of experiment 5 is 0.5 times 10 to the minus second. That has to equal whatever K is times the concentration of A, 0.5 to the 0th, times the concentration of B, 0.6 to the first. Well, if I want K by itself, 0.5 to the 0 is simply 1, so that's gone on its own. But if I divide by 0.6 on both sides, I can get rid of this whole expression. So K is simply 0.6 dividing 1.5, which comes out to be 0.025. In order to determine the units, you can think of it mathematically. Rate is molarity for each seconds, or molarity seconds to the minus 1. Our units of K have to give us those units. Molarity as a numerator, seconds, or time in the denominator. So time will always be in the denominator. Time will always be to the minus first. How many molarities there are depends upon the overall order. Since each of these is a concentration, we need to cancel out those concentrations. So the units of K are always going to be a negative molarities, a negative time, or molarities and time in the denominator. How many minuses, how many molarities you need in the denominator depends on the overall order. The overall order is to add up all those exponents. So the overall order for this reaction is 1. So molarities is raised to the first if I need to end up with molarities as a numerator. I technically already have it in the expression. So molarity is raised to the 0 in this answer. Now you can think of it mathematically that way. Here's a shortcut. If you hold up your hand and put a finger up for each molarity of the overall order. So the overall order of this reaction being 1, take 1 away, the overall order minus 1. The overall order minus 1 is negative, what you need to raise the molarity to. So the overall order of 1 minus 1 is 0. So I raise molarity to the 0th power, or therefore I just remove it. So the units of K here is simply time to the minus 1. Time being seconds, minutes. In this case, it's hours. So our units here are hours to the minus 1. Exercise 5 has us find the order of the reaction with respect to this complex ion here. Now, since we only have one reactant, we don't have to worry about the consistency of one versus the other. So you can do either table logic or algebra to determine the order with respect to the complex ion. Table logic wise, in experiment 1 and 2, we see simply that the concentration doubled and the rate therefore doubled, so it must be first order. By algebra, we set up experiment 2 to experiment 1. Experiment 2 as the numerator, as the concentration is larger, makes for easier math. 10 to the minus 7th cancel out. 2.6 divided by 1.3 is 2. Has to equal our constant, which cancels out. 10 to the minus 7th cancels out. 10 to the minus thirds will cancel out. And our constant cancels out. So 2.6 divided by 1.3 is 2. 2 divided by 1 is 2 raised to some value. Therefore, M must be 1. So the reaction is first order. So our rate law would be the rate equals K times the concentration of our reactant raised to the first. To determine the value of K, we will divide by the reactant on both sides, so the rate over the concentration of the reactant raised to the first has to equal K. And we can choose any experiment. As we didn't use experiment 3, might as well use it here. So 3.9 times 10 to the minus 7th over 3 times 10 to the minus 3rd to the first has to equal K. We get a value of K of 1.3 times 10 to the minus 4th. We need units for our K. So the overall order is 1. 1 minus 1 is 0. So molarity will be raised to the 0. And our unit of time is always in the denominator. So time to the minus 1. Time here being in minutes. So molarity raised to the 0 we don't put, but our units of time needs to be in the denominator. So 1.3 for every minute, or 1.3 for minutes to the minus 1. Exercise 6 is a little more challenging as there are 3 reactants. However, the overall process is still the same. Please pause the video and do exercise 6. For the bromate ion, we determined it was first order because in experiment 1 and 2, the concentration of the bromide and hydrogen ions is constant while the rate doubles when the concentration doubles, therefore it's first order. For the bromide ion, experiment 2 and 3 shows the bromate and hydrogen ions constant. When the bromide ion doubles in concentration, the rate doubles in concentration, and therefore it is first order with respect to bromide. In experiments 1 and 4, the bromate and bromide ions are constant, while the hydrogen ions double, and therefore the rate quadruples, so we now know that it is second order with respect to the hydrogen ions. No matter how you derived your answers, the rate would be the constant times the concentration of the bromate ion to the first, times the concentration of the bromide ion to the first, times the concentration of the hydrogen ion to the second. The overall order would be 1 plus 1 plus 2, or 4. And the value of the rate constant, we simply plug in. To find the value of K, I'll divide by bromate, bromide, and hydrogen squared. And plug in any experiment. So I'll use experiment 1, for example. To determine that the value of K is 8, and our units of K are always going to be our unit of time, in this case seconds to the minus 1, molarity raised to the negative overall order of 4 minus 1, which is a negative 3. So molarity to the negative third. With that being said, you can do page 26 in your packet, which gives you lots of data. You are to determine the rate law, the value of the rate constant, and its units for each one. Please pause the video and complete page 26. If you're feeling fancy and dancy, you can also attempt page 27. Now, when a reaction occurs, it's normally in steps known as mechanisms, a series of reactions that occur. Remember when I started this, I said the order of a reaction was how each reactant held up that reaction. If you're making peanut butter and jelly sandwiches for lunches, your job is to spread the peanut butter and the jelly. Your sister's job is to fold the sandwiches together. And your dad's job is to put them in bags. Your step takes the longest. You are limiting the reaction. You have to spread the peanut butter. Your sister's got to put them together. Your dad's got to put them in bags. You are part of a mechanism, and you're the rate determining step. Now, overall, the reaction occurs the same. You are making one sandwich for each bag, but the rate law is ultimately determined by the steps involved, where the slowest step, the rate determining step, is really the only thing that's in the mechanism. So everything up to that point will include in our rate law, but then after that it's irrelevant. So anything usually to the 0 power is probably not in the rate determining step. All of this being said, it must be done experimentally, so I will always provide you mechanisms and ask you to either support or reject them. Do they match the stoichiometry? In the end, when you add up everything, do you end up with the reaction that you started with? And does it agree with the rate law that you determined in a previous part? Now, when we talk about these, we'll talk about their molecularity. How many molecules are involved? So if you have only one molecule involved in your reactants, that's unimolecular. But if there are two involved, that's bimolecular. For each reactant in that step, it goes into your rate law. If you are the rate determining step, obviously you are in the rate law. However, if your sister's spreading the jelly and you're spreading the peanut butter, then you both are part of the rate law. But if it's just you, you have to spread the peanut butter, you have to spread the jelly, clearly you are slowing down the reaction the most. So you would appear twice. And they're cumulative. So if the rate determining step occurs here, then the rate law would be 2 A's and a single B. Anything that happens after that, your father putting them into bags, is not going to be part of our rate law. So here is a possible mechanism for how hydrogen and nitrogen monoxide produce nitrogen and water. It asks us to state the molecularity of each step and then sum them up to show how they yield the net reaction. So, easiest part first, the molecularity of each step. How many molecules are in the reactants? So since there are two molecules in this in step 1, let's say, we're going to call that bimolecular. Now step 1 leads to step 2. So 2 nitrogen monoxides produce dinitrogen dioxide. That is then immediately consumed. So it's what's known as an intermediary. Think of it kind of as the knife in the spreading of the peanut butter and jelly. Is the knife really part of the process? No, because you get to use the same knife over and over again. Intermediaries are not really part of our mechanism, so we're going to remove it. So this next step actually only has one reactant in it. It's unimolecular. Now that step produces dinitrogen monoxide and a water. That dinitrogen monoxide is another intermediary, so it also is unimolecular. The knife is not really part of the overall process. When everything is added up and you've removed things that are on both sides of the equation, you should end up with the reaction you started with. So from that first step, I have 2 nitrogen monoxides. In the second step, I have a hydrogen. In the third step, I have another hydrogen. So 2 nitrogen monoxides and 2 hydrogens produce dinitrogen dioxide is produced and then used. Dinitrogen monoxide is produced and then used. So the only thing I have as product is a water, a nitrogen, and another water. And sure enough, that matches the stoichiometry. If we were told the rate or law of this reaction was rate equals K times the concentration of nitrogen monoxide squared, and we're asked where is the rate determining step, this actually would tell us where the slow step is. The slow step has to be in line with the rate law. This rate law says that nitrogen monoxide is the only player in this reaction that determines the rate. So this must be the slow step, and the other two must occur pretty fast. So two nitrogen monoxides colliding must have been the slower step. If the rate law was something different, like say it was the rate equals K times the concentration of nitrogen monoxide squared times hydrogen, the slow step would have to be the second in the mechanism, because that matches our rate law, where you have two nitrogen monoxides have to collide, and then they have to find another hydrogen to match up. So the next one says, here is a rate law, here is a reaction. Is this mechanism satisfactory? Does it meet both requirements, where it matches the stoichiometry and matches our rate law? So by saying that the slow step is right here, only these two reactants raised to the first can be in our rate law, and therefore that matches. So at least one of the requirements is satisfied. Is the overall stoichiometry satisfied? The fluorine free radical would cancel out, and so two nitrogen dioxides, fluorine gas, producing two nitrogen dioxides, monofluorides, matches as well. So yes, this mechanism satisfies both the stoichiometry and the experimentally determined rate law. So it is a valid. If we were given possible mechanisms, we can use the stoichiometry and our experimentally determined rate law to determine which of these mechanisms would satisfy both requirements. In mechanism 1, we end up with 2x plus y gives us a z, which matches the stoichiometry. However, with the slow step being in step 1, our rate law would be first order with respect to x, and that does not match the experimentally determined rate law. So mechanism 1 is invalid. Mechanism 2, we have x and y giving us z. That does not match our stoichiometry. So mechanism 2 is invalid. Only mechanism 3, where m and n are both intermediaries, giving us 2x plus y gives us z, matches the stoichiometry, and with the slow step being step 1, the rate law is first order with respect to y. So only mechanism 3 is valid. Now with that being said, we are done with differential rate law, determining the rate law from concentration and rate data. Next class, we will take a quiz where I will ask you to determine the order of the reaction for each reactant. Tell me the overall order. Use stoichiometry to tell me the concentration of the reactant at a given point, and then justify a particular mechanism. So please find some free responses, or I will provide you free responses to practice that, and I will see you next time when we talk about integrated rate laws, which is when I provide you concentration and time data, and there will only be one reactant. However, you need to analyze a graph. Things can be so while that's easier on paper, it requires a little more thought on your part. I will see you next time.